Yeah, maybe we can start now. Hi, everybody. Well, I'm very happy to introduce Professor Choi, Kyeongsu Choi from Kias, Seoul, Korea. And well, let me tell you a little bit about him. So he got his PhD at Columbia University on the guidance of the Professor Daskalopoulos at May 2017. And he was a CLE Moore instructor at MIT during September 2017 to May 2020. And then from then, he's a professor at the Korean Institute for Advanced Study. And then today, he's going to talk about the ancient mean curvature flow and singularity analysis. Please welcome the speaker.
Thank you for a kind introduction, and thank you for giving me a great opportunity to give such a nice seminar, Aishan PD seminar. And then especially, I love that you can pronounce my family name correctly, Choi, which is impossible in general in the Western world. Anyhow, so let me talk about ancient mean curvature flow and its application to singularity analysis. So the mean curvature flow is kind of evolution of hypersurface. Here is the immersion of some manifold to Rn+1, but you can imagine that each image must be a hypersurface. And then we want to see a solution to this geometric heat equation. Sure, this is a vector value anyhow. Then we can consider the family of the images, which is the evolution of hypersurface, and we call this as a mean curvature flow. And especially the reason we call this as a mean curvature flow is that the Laplace of the position vector x is negative h dot nu, where nu is the outward pointing. So negative nu means it's just an inward pointing. And then h is the mean curvature. So this flow moves in when that is convex with the speed of the mean curvature. So we call this as a mean curvature flow. And sure, this is a kind of geometric equation. So for the PD person, if we just consider the case that x is the graph of a function on Rn, then that u satisfy this degenerate quasi-linear PD. Yeah, just parabola equation. And then, yeah, we are interested in singularity of this flow. So when my initial data is around the sphere, everywhere I have a unit, the same speed, because the sphere has the same curvature everywhere. So it shrinks in with the same speed. So it remains as a round sphere and getting more small, it shrink, and it converges to a point. However, to see the singularity, we may dilate the picture in this way. And then we can see that, okay, it might be just a static round sphere. So we call this is a Rescaled one, where this is the original mean curvature flow. Similarly, if we consider this kind of initial data where the initial data looks like a dumbbell, then you can see that we have a high curvature in this neck. So in the neck, we have a high speed compared to the other part of the. So the neck develops shrink faster than the other part. So it will develop this kind of singularity and get this connection. And we have some solution beyond through the singularity, hopefully. And then to see this singularity, we blows up, we dilate the solution. Then you can imagine that this singularity will converge to a round cylinder. Especially, here the curvature goes to 0, and this goes infinitely small cylinder. So this compact part goes to infinity. So we only able to see this flat, the round cylinder. And here the important thing is this: the round shrinking sphere and the round shrinking cylinder are both self-similarly shrinking solutions. So as like a general, the other parabolic PD, if we do the blow up, we may have, you can expect that it might converge to a self-similar solution. Indeed, there is some theory. So, well, say that X naught T naught is a singularity, and then we may consider a rescaled mean curvature flow, which satisfies this equation, and it can be defined in this way. Yeah, this is just a question. No, okay. Yeah, and then if we consider this rescaled mean curvature flow at this singularity, then we have this kind of a monotonicity formula. Yeah, it is just a hit corner, right, of the parabolic equation. And then, well, it satisfies this nice monotonicity, and then you can imagine that, okay, at the singularity, this quantity would converge to 0. And actually, this comes from this vector dot nu, the normal vector, which means that if we just consider normal directions, then at the singularity, this would go to 0. So sure, moving along tangential direction is actually nothing. Yeah, whatever. So we can in fact expect that rescaled mean curvature flow converges to some solutions that's phi 0 equal this. And we call that kind of solution as a shrinker. And what is a shrinker again? If sigma is a shrinker, then if I just multiply this function root tau as sigma, then that is a solution to the main curvature flow, which means this is a self-similarly shrinking solution. So we call this a shrinker. And then this one would converge to a shrinker. Well, maybe I'm so fast. I don't know. Maybe you can ask any question because this is a Zoom seminar. So maybe I talk so fast compared to chalk seminar. But yeah, and then here the point, important thing is that we only know that this rescaled one converts to a shrinker with multiplicity. So what is a multiplicity? This is a bit geometric term, so let me explain some example. So okay, here I have a sphere and the other sphere in and out, and then let me connect these two spheres by an X. And who knows, probably these two spheres convert to a more and more round sphere, and then maybe this red next degenerate to a point. Then maybe unfortunately, this solution, this mean curvature flow, may convert to a round sphere with multiplicity 2. I mean, just a 2 same round sphere with some point singularity. So here, the convergence means convert to a shrinker with a multiplicity in measure sense. So except some measure 0 point, that would be converged to a shrinkers. Well, actually, we don't know whether there is an example of singularity with multiplicity. So there is a so-called multiplicity 1 conjecture that any closed mean curvature flow do not develop singularity with multiplicity. that is a conjecture. And somehow it makes sense. And there are some analog conjectures in minimal surface. And indeed, nowadays, from index theories, I mean, minimax theories, gave us some the result for the multiplicity one conjecture in the minimal surface. But let me skip about the multiplicity one conjecture in this talk. There's a totally different topic. Okay, then. Rather than just a rescaled mean curvature flow, I would like to introduce some limit flow, tangent flow, and ancient flow to analyze the singularity. So again, let me consider this x naught, t naught is a singularity, as like this. And let me consider a sequence of space-time point xi and ti, and some parameter lambda I. And here lambda is just a positive number, and this sequence of lambda i's diverges to plus infinity. And then I just consider these parabolic dilations. So I have a sequence of mean curvature flow. And then in case this sequence of mean curvature flow converges to certain mean curvature flow, then we call that as a limit flow at the singularity. And in particular, if we choose these xi, ti's as the same point, the singularity, then we call this is a tangent flow. Yeah, and then you can imagine that because we keep dilate this given mean curvature flow with a larger and larger parameter. So this xi exists for longer and longer time, and they all end up with t equals 0. So the limit must exist from negative infinity by definition. So in general, the solution to parabolic PD, which exists from negative infinity, is an ancient solution. So limit flow is an ancient flow if the limit flow exists. And then as you know, this ancient solution to parabolic PD is similar to entire solution to elliptic PDs. So we can expect some parabolic Weber type theory. So under some reasonable conditions, we may expect some classification result. So we may able to classify all potential singularity, singularity model of the flow. And then let me just point out some actual difference between limit flow and the tangent flow with some example. Sorry, I forgot to write down that, but well, in the case of tangent flow, by using this previous rescaled flow argument, we can show that, okay, tangent flow would converge to a self-shrinker. Not a static, some self-shrinker, some rotating self-shrinker as tau goes to negative infinity, backwards negative infinity. So yeah, through the tangent flow, you can only able to see the self-shrinkers, not some the other types of solution. However, in case of this limit flow, we can actually see the translators. Otherwise, in general, some PD people say this is a traveling wave, right? So, for example, there is some certain translators, so-called Ball translator, whatever. There is this kind of rotational symmetric hypersurface which translate with unit speed, by the mean curvature flow. So this is just a traveling wave, but we call this as translator. And then actually these translators can be the limit flow as singularity. For example, this is an example of Angen and Velasquez in 97. So maybe I can consider some rotational symmetric mean curvature flow, but very interestingly and or unfortunately, we can construct this kind of neck. I mean, this kind of singularity. I mean, actually, this part has very high mean curvature compared to other part. So this one would develop a point singularity. And we call this is a degenerate neck. Maybe you can see more pictures in this paper. Anyhow, then if I blow up this singularity, then this part would converge to this Bose-Soliton. And always this Bose-Soliton means rotational symmetric translator. Anyhow, this is just an example. So in short, tangent flow is a special types of a limit flow, and limit flow must be ancient. So if you classify all ancient flow, then you can find all limit flow and tangent flow, whatever. Okay, now let me talk about application of the singularity analysis for topology. So the rich flow has been studied for Poincare conjecture, and yeah, we still work for the four-dimensional rich flow for four-dimensional smooth Poincare conjecture, which is still finite. Similarly, well, there might be many applications of mean curvature flow, but Chompley's theory or Chompley's problem would be an excellent application of the mean curvature flow for topology. So yeah, there is a very obvious Chompley's theory. So maybe that is discovered in 100 years ago. So if you have a closed curve, not a closed curve. Yeah, closed curve embedded in the plane. What? Sorry, I have to change. There are so many typos. Okay, let me change here. So there is a closed curve embedded in the plane, which bounds a disk, right? Which bound the disk. Then that is a What? I'm sorry. Let me without this sentence. Let me just explain. So if you have a closed curve embedded in the R2, then it bounds a disk, which means the curve is a boundary of a disk. Bound means that is a boundary of something. And there are some natural extensions. So in 3D, maybe one can ask that if there is a closed surface embedded in R3, which is homeomorphic to a sphere, then does the surface bound a ball? I mean, does the surface is a boundary of a 3 ball? Well, interestingly, no. There is a counterexample, so-called Alexander's horned sphere. Well, let me show you the Alexander's horned sphere on Google. So, because of copyright, let me just show this image on the Google. Maybe you can Google it. So this is maybe the image in the Wikipedia. This is the Alexander horned sphere. Well, it is constructed by topologists, so I don't understand. But anyhow, they say that, well, this red guy, this orange guy is topologically sphere. And clearly it does not bound the ball. So anyhow, there's an interesting counterexample, even though I don't understand why that is a counterexample. But, well, fortunately, if the surface is smooth, I mean, if ferromorphic to S2, then there is a boundary of a 3 ball. Okay, it sounds natural. Okay, and then the conjecture is a 4D case. So if you have a closed hypersurface embedded in R4, which is ferromorphic to S3, then does the hypersurface bound a 4 ball? yeah, this is an open problem. So maybe we can add some extra conditions. I mean, the goal is just to prove the Schoenflies problem, but maybe we can just add some conditions like mean convexity, the positive mean curvature, or some certain, I will interest what is entropy. I mean, entropy bound, whatever. So maybe there would be some condition to make this statement is true. Because I heard that many topologies trying to construct a counterexample. So who knows? Maybe they maybe in the future they can find some counterexample. Then maybe for geometers we can find some sharp enough conditions to make this problem is true. But I don't know. It is still open. Yeah, no one knows whether this statement is true or not. So anyhow, so the main curvature flow, yeah, clearly changed the topology of the hypersurface, the solution, through the singularity, right? For example, let me see. Yeah, like this. This main curvature flow develops singularity here, and it gets disconnected. So the topology has been changed. So in this way, through the singularities, we may expect some nice change of topology. And especially now, this is a parabolic PDE. So the blow-offs were the self-stimulus, self-shrinkers. And then hopefully we can classify all self-shrinker to see the topology changes. Well, but it was the hope. But soon we realized that there are infinitely many shrinkers. So, well, unfortunately, if we just consider mean curvature flow, then we cannot classify all self-shrinker, and then we cannot study the topology changes through the singularity. Then how should we do? Then the next step is to consider stability. Okay, so we know that some flow, the mean curvature flow, converges to a self-shrinker at the singularity after rescaling. And then, yeah, if we consider self-shrinker, then we consider the linearized operator L of the shrinker. And then the geometers sometimes call this is a Jacobi operator, that is a linearized operator. And then unfortunately, this operator is always has unstable eigenfunctions. First of all, the mean curvature H is the unstable in this way. And all the coordinate vectors of the position are also unstable. But according Minikochi introduced the entropy of the mean curvature flow in this way. So it looks like a heat corner again. So they use the monotonicity formula of the Foucault strongly. But the point is, we can consider or screen on further hit this of this quantity for all center and dilations. And then, indeed, this the unstable function from coordinate function came from wrong choice of rescaling center, right? For a given mean curvature flow, we may choose some the other center, which may be another singularity, right? We can choose a random point, which is another singularity. Then you can imagine that the rescaled flow at the wrong choice center would not convert to a self-shrinker because we choose the wrong center. So this coordinate function came from the wrong choice of the space center, and this H come from the wrong choice of the space center. So it comes from the dilation problem. And then if we just consider this entropy, and then we can consider this H and X, as sort of a null function, like yeah, because they actually came from the. We can kill this. We can somehow ignore this unstable eigenfunctions by considering this, by changing the centers and the dilations. So maybe the natural concept for a linearly stable shrinker would be the shrinker whose Jacobi operator has the H and coordinate function as the only unstable eigenfunctions. Yeah. And then actually they shows that hyperplane spheres and cylinders are the only shrinkers whose Jacobi operator has unstable eigenfunction H and coordinate function. Yeah, they are the only unstable eigenfunction of the Jacobi operator. And especially, yeah, these results strongly use the result of a Rescaled naturally, which is that a shrinker with positive mean curvature must be a round sphere or round cylinder. Actually, yeah, you know, if you know that your shrinker has positive mean curvature, then this H is positive eigenfunction. So it must be the first eigenfunction. So this result will be very helpful to classify this kind of a linearly stable shrinkers. So yeah, we know linearly stable shrinkers. Then there are some conjecture then. So the other shrinkers is somehow unstable. We can expect it. So we can make a conjecture that if I have some given closed smooth hypersurface, and we can perturb it very little, so we have an epsilon graph of that given hypersurface, so that the main curvature flow from this perturbed initial data develops only finitely many singularity, which round sphere and round cylinder, and with multiplicity 1. Sorry, I forgot that. The round sphere and round cylinder with the multiplicity 1. And then we call this well-chosen mean curvature flow as the generic mean curvature flow. So for the topology, it is enough to consider the generic mean curvature flow because the epsilon graph of the given hypersurface share the same topology. So to cleanse up the conjecture, we need several steps. So multiplicity 1 conjecture is something I explained. Now we have to show the well-posedness around the linearly established singularities. Yeah, because again, like this picture, through this cylindrical singularity, we need to assure that this flow stays well-posed. So we need the well-posedness. And then we need to show that actually by choosing the generic mean curvature flow, we can avoid unstable, linearly unstable singularities. And then finally, somehow by choosing well to perturb the generic mean curvature flow, we want to isolate the singularities. Yeah, if isolate is accumulated, it is very annoying to analysis, especially in higher D. 3D is fine, but 4D is terrible. So we need these conjectures. Then up to now, we have some progress for second step and third step by using the ancient solutions. So let me quickly talk about the well-posedness. So indeed, there are some ill-posed example. In the 1D case, we have a clear example which actually exists. But higher D, we have some ill-posed example. I mean, there's an expected example. We don't know whether there is such a solution or not. Because there exists I mean, we expect, we don't know, a self-shrinker with these two conical ends. Yeah, this is obtained by computer numerically, and we didn't prove it. We don't know how. Yeah, we don't have any proof for the existence of a self-shrinker with these two ends. Yeah, we don't know, but yeah, we expect that exist. And then you can see that if this shrinker shrink, then it would convert to this cone at the singularity. And then through the singularity, we expect infinitely many solutions. For example, well, say here's a blue guys, and maybe we can expect this blue solution, which get this connection. Or if you consider this red guys, maybe we have this kind of solutions. Sorry, my picture is bad, but then yeah, if you have a conical singularity, then through the conical singularity, there are infinite many solutions. Indeed, we don't know whether there is such a shrinker or not, but we know that if our initial data is actually looks like this, then there is an infinity many solutions starting from the cone. Yeah, even though we don't know there is some solution convert to cone or not. But in the 1D case, we have a clear example. Wow, but 1D is weird. Okay, anyhow. So to attack this well-posedness, I would like to record the result of pre-scan study I just mentioned. So what they show is that mean curvature flow with positive mean curvature has multiply one spherical or cylindrical singularities. So this is very nice. So conversely, we can make a conjecture that mean convex neighborhood conjecture, which is that if the mean curvature flow has multiple one spherical or cylindrical singularity, then there is some space-time neighborhood. This is not a parabolic neighborhood. We consider the time period beyond the singularity, right? So this is just a space-time neighborhood. And in this neighborhood, maybe the mean curvature flow has positive mean curvature. Okay, and then actually this mean convex neighborhood conjecture is very important because Hershkovich and White shows that if this conjecture is true, then the bracket flow, which is a weak mean curvature flow, sort of, yeah, this is defined in the geometric measure sense, so GMT sense. And yeah, this bracket flow is well posed in a space-time neighborhood at that singularity. Yeah, this is because if we have a mean convex neighborhood, then mean curvature is positive, which means the flow has positive speed. So in that neighborhood, the flow foliates out. So the flow moves monotonically. So it does not go and back, whatever. And then it somehow foliates some space. So by using those kind of monotonicity, you have a well-defined solution, well-posed solution in measure sense. There's a key idea. So one should consider positive speed for well-posedness. And yeah, and then in particular, I mean, so this conjecture implies the well-posedness theory. And then in particular, if the all limit flow at the singularities are convex, then this conjecture is true. So it is enough to show that all limit flow cylinder or spheres are convex. Then we have well-posedness. So there are some history. So actually, that conjecture has been settled in R3. And people start working for the R4 case, the most important case. And let me shortly mention about how to do that. So first of all, coding Minikochi shows that tangent flow at those kind of singularities are unique. So what this means again. So we know that tangent flow, I mean, sphere case is so simple. So let me just consider cylinder case. So we know that tangent flow converts to a cylinder subsequentially. So it may look like a cylinder, but it rotating very, very slowly. Yeah, that might be possible. So one first need to show that the tangent flow must convert to a fixed static cylinder. This solved by Kochi in 15. And then Angen and Daskalopoulos session shows that well, two convex. So two convex means that you have some principal curvatures of hypersurface, and then if you choose any two different principal curvature and add them, and the sum is positive, then we call this is a two convex. Sorry, this is quite artificial condition, I know. But two convex is just a mean convex in R3 case. So this is nice enough. Oh, yeah, this is, sorry, there are some. So strictly two convex and convex. Their statement, I forget, sorry. This is a, yeah, anyway. And then non-collapsed. Non-collapsed is also some nice condition, but let me skip the definition. You can see that Brian White or Andrews' paper for the definition of non-collapsedness. So anyhow, for a certain reasonable condition for singularity model, just a convex closed ancient mean curvature flow must be a round sphere or an ancient oval. An ancient oval looks like this. So it has a rotation symmetry, and the two ends looks like a ball soliton, and then as time goes back, this is getting longer and longer, and then the middle looks like a round cylinder, converted to a round cylinder. But anyhow, it must be round sphere or an oval. And then Brandon and myself shows that if we consider complete case rather than closed, then it must be a ball soliton. Yeah. And then anyhow, and then finally myself and Hastrofer and Hershkovich shows that if ancient flow converges to a round sphere or round cylinder at the backward infinity, which means that is a singularity model from the spherical or cylindrical singularity. And then they must be sphere, cylinder, or oval, or soliton. So, yeah. So the potential or limit flow from this singularity must be same to the least of this convex case. So, yeah, and then, yeah, jointly with Brian White, we extend the result for the cylinder in hierarchy as n-1 cross R case. So it is still open that classification. So it is still open to classify the ancient solutions from S1 cross R2 in R4 and some higher dimensional R case. Yeah. Okay. Let me talk about how to classify this later. Then I don't have enough time, so let me quickly mention how to consider avoidance. So actually, Lu Wang and then Jacob Bernstein consider this avoidance first. They have many papers. And then, yeah. So anyhow, basically, they establish some methods to avoid multiplicity 1 compact or asymptotically conical self-shrinkers with the multiplicity 1. And then I myself and Chodosh, Mantudalins, and Shurse provide some alternative way for their alternative proof for their theory by using ancient flow. There's the main difference from previous argument. Yeah. And then how we use the one-side ancient flow. One side means that if you have a self-shrinker, then yeah, you can consider static shrinker. And then one side ancient flow means that some ancient flow which is state in one side of the shrinker, right? The shrinker divides the space into two regions. And then we may consider the flow do not touch the shrinker, so they stayed in one side. And then, yeah, we can show that the one-side ancient solution is unique and it has positive speed after rescaling. So here, positive speed means the speed of a rescaled flow. So h minus a half x nu is positive, different from positive in curvature. But still, we can use the result of a Hurst curvature and white. So positive speed means that the flow only develop multiple one spherical and cylindrical singularity. So stable singularities. Okay, and then how to use the one-sidedness. So if you consider generic mean curvature flow, whose initial data does not touch the given data initially, then you can imagine that if you have a given initial data and the other part of the initial data, which does not touch the initial data, given one, then by the maximum principle, they never touch, right, up to the singularity. So if you find some conical or compact unstable singularity, and then as the first singularity, you blow up the unstable singularity, and then you can see that our perturbed solution become an ancient flow, but it still does not touch the self-shrinker, the tangent flow of the given singularity, given flow. And then, yeah. That we know that ancient flow is unique and then it has positive speed. So that's kind of well posed and very nice. So we can choose close in some generic mean curvature flow whose which convert to a one-sided ancient solution around the singularity of given flow. I mean unstable singularity of given flow. So we can avoid those kind of conical compact singularity. Okay, let me quickly talk about this and how to prove it. So let me consider rescaled mean curvature flow. Then we can consider the flow as the graph of a function defined on the shrinker. And then the function satisfies this kind of a linearized equation. U tau is LU, linear operator, and quadratic error. So this is just error. So we can expect that the U behave like a solution to linear equation. And then linear equation, solution to this linear equation looks like this by just a ODE in the intro to PD course. Yeah, and then by using the, and you know, we expect this U convert to 0. So this C must be 0 when this phi is stable because it goes to infinity as tau goes to negative infinity. So by using the Merle-Zaag ODE lemma, actually ADS figured out we can use that. So yeah, ADS is a kind of pioneer of this spectral point of view of ancient solution. We can show that the U actually looks like, yeah, there are some leading eigenfunction in the eigenpair time function and then some constancy times error. And especially when this lambda I is 0. So I mean, if this is a kernel, then this time function will look like a 1 of tau to the power. And in particular, in case I equal 1, then first eigenfunction is positive. So you can see that U tau must be positive. So this was the idea of this paper. I mean, yeah, to be one-sided, this U must be positive everywhere. So which means this leading eigenfunction must be positive. And then positive eigenfunction must be the first one. And then in that case, we have uniqueness. And then its derivative must be positive. Well, there are some similar case, but well, this is a specific example, and maybe I'm out of time. So maybe I can stop here.
Okay, thank you. Do you have any questions? So if you have a question, you can click the raise hand. And, well, maybe I can ask one question. Like you talked about the multiplicity one. Do you have a question?
Yeah.
Multiplicity. Yeah, go ahead. Yeah.
No, you go ahead first.
Okay. So you discussed about high multiplicity solutions.
Yeah, yeah.
Can you talk about a little bit more about high multiplicity solution in minimal solution, minimal surface?
Yeah. So in the minimal surface, let's consider S3, and then in a great circle, the S2 is a minimal surface, pure unstable minimal surface. And then actually there are some example that there is a sequence of surfaces which converges to a multiplicity 2S2. I mean, there are some, you can consider 2S circles, S2, around the gray circle, and you connect them by some necks.
Okay.
Then if you add more and more necks, the minimal surface with those kind of many necks getting close to multiplicity 2S2. So in this example, to find the sequence of minimal surface converted to multiplicity 2S2, you have to keep add more and more necks.
I see.
Yeah, but fortunately in the main curvature flow, yeah, we should not change the topology until the singularity. So we expect there might be, we might do not have those kind of example. We should free, but I don't know. This is a big condition.
Okay, okay. Yeah. Okay, maybe Julie, you can ask a question.
Oh yeah. Can you do a proof of the 3D smooth Schoenflies conjecture or Schoenflies theorem with mean curvature flow?
We don't have yet. Yeah, because first of all, yeah, the 3D case is just proved by topologists. So a lot of people do not know the proof of this theory. And then the main problem here is, okay, well-posedness is fine. We have proved. Avoidance is almost done, I think. We don't need to isolate. The D3 is fine, I think, but the problem is multiplicity 1 conjecture. So unfortunately, we still don't know if the multiplicity 1 conjecture is true or not in our 3 case.
I have a follow-up question too. What would happen if you hit some approximation to the Horn sphere with a mean curvature flow?
Yeah. Well, Horn sphere is too complicated.
Right.
I don't know. Yeah, I don't know. Sorry. Yeah. Yeah. Yeah, that will be interesting, but well, maybe, yeah, there will be good approach. I don't know. Yeah.
Is there any other question? You can click the raise hand. Okay, so if there is no question, so we would like to say thanks to speaker again. Thank you. And there will be a coffee break.
There's a question. There's a question.
Oh, there is a question.
Yes,
Oh, that's great.
Professor Kang has a question and has allowance to speak, actually.
Okay. Please.
Hi, sorry, yes, I raised the hand and then I quickly just lower the hand again. But could I just ask just a quick question about Schoenflies problem in 4D?
Yeah.
Is there any development in that side, in that direction?
Oh, okay. First of all, for the okay, I heard that topologists keep trying to construct some counterexample. So I heard that David Gabay at Princeton working hard about that, and he made a great progress for certain, I don't know. Yeah, anyway, maybe you can find some papers, recent papers of David Gabay for the counterexample case. And then for the flow people. So if you assume that the initial data has two convex initial data, then it must develop as 2 cross R1 singularity, and then we can show that this problem is true, this statement is true. And second, if it satisfies, if the Minkowski flow has low entropy, why is low entropy is that the entropy of the Minkowski flow is less than the entropy of a round cylinder as 2 cross R1, then it is again or not. So the statement is true. So for the more details proof, you can see the paper of Wang and Bornstein this year, or my paper with the Chodosh Mantulichers this year. Yeah.
Okay, great. Thank you.
Thank you.
Okay. Any other question? Okay, then let's just say thanks to speaker again. And we're gonna have a coffee break right after this seminar. And probably you got the email from the Daniel. Please click it and then join the coffee break.
Yeah.
Okay, thank you.
Okay, thank
Bye,
you.
everybody.
Bye.
Bye.
Bye. I close the meeting.